So the simplest equation, your actual ET for your crop, the actual amount of water that you're estimating you lost, is the calculated ET reference times your crop coefficient. Some adjustment, either a little bigger to a little smaller than 1. So KC, or the crop coefficient, is average or mean crop coefficient incorporating crop characteristics and averaged effects of soil evaporation. You're estimating, you're making a best guess, but there's a lot of data out there. There's a lot of crop coefficient charts, etc. For normal irrigation planning and management, hydraulic studies, etc., the mean crop coefficients are applicable and easier to apply than the dual crop coefficient approach. And so the dual crop coefficient approach, you're looking at a coefficient for your crop plus the stress. You can use a 2 or you can use just 1. And here, or excuse me, anyway, I'm not going to get into the dual crop coefficient. Not going to worry about it at all. You can incorporate the stress into your crop coefficient and use just one number. So actually, you can have this where the stress is included in the crop coefficient, or you can separate out your crop coefficient and the crop stress coefficient into 2 separate things, but you still have only one true crop coefficient. And there are models with having dual crop coefficients that don't worry about it. Don't worry about it. It does complicate things a little bit. It can be more accurate in some situations. If you really get into this and into the weeds and you really love this concept and you want to fine tune your irrigation, I would suggest doing some reading, playing around with it, talking to people, what are they doing? But keep in mind, this is just one piece of the puzzle. I not only want to look at and find my best actual mathematical estimate of my actual crop evapotranspiration to estimate how much water I really lost, but I also want to measure directly the water stress in the plants themselves by doing a pressure bomb test if it's a permanent crop like grapes or something, or almond orchards or something like that. I'm not going to worry about that too much if I'm growing lettuce or spinach, unless it's for research purposes. But I'm also looking at soil moisture. You might have aerometers, which is a brand name of these tensiometers checking water tension or water availability at the soil, or other types of water probes that can measure water. And you're putting this together as a package deal. You're looking at your evapotranspiration, you're looking at the soil probe information to tell you what the soil says the water availability is, and you're looking at actual water stress in your high value crops like wine grapes, orchard crops, or other permanent crops, less so in the short-lived annual crops like the lettuce, spinach, broccoli. They're not in the ground long enough to really worry about getting leaf stress data on the crop itself. So alfalfa or grass are the reference basis. I've already mentioned that. There are definitely different methods, different mathematical models, and there are issues about moving these different models to different areas. You can't just say, hey, we've developed this perfect model that works really good in Salinas, we're going to use it in Florida. Doesn't transfer necessarily. And so there are issues with the models and the types of gross climatic data that you might have in different regions. So I'm not going to worry about the details here. Just you know that alfalfa and grass are reference crops. And you can look up some of the specifics about the grass coefficient and the alfalfa coefficients. Geographical transferability. Evapotranspiration of well-watered crops is mainly dependent on available energy. The geographic transferability requires assessment of and often adjustment for differences in growing period conditions between development and application sites. So if you move to different sites, you have to tweak things. You need to adjust it. You need to do some data. You can't just take these mathematical models and assume they work everywhere. So transferability specifically means, or the mean crop coefficient requires the assessment of irrigation and rainfall patterns. So you need to look at the differences of available water going into your growing area, into your field, as major contributors to geographic differences. Climate differences between the sites, like wind and humidity especially, also have major impacts on the transferability of these crop coefficient data. So you need weather. You need a good weather station. Now we have something here in Salinas and, well, through California, called the CIMIS, the California Irrigation Management Information System, CIMIS, CIMIS. And the CIMIS stations are scattered, a couple hundred of them, all throughout the agricultural regions of California, and they have soil temperature, air temperature, solar radiation, relative humidity, wind direction, wind speed, rainfall. All of the important data are being collected. And here's one of those stations with the major meters labeled on this slide here. The only thing that I don't see is soil temperature listed on this particular presentation. Different models may or may not use soil temperature characteristics. It depends. Weather data intended for the reference evapotranspiration estimate should be collected at weather stations sited over well-watered, clipped green grass surface in open irrigated settings. So we have a CIMIS style or CIMIS capable sort of weather station at the Alisal campus, but it's located in the wrong spot, and it's on the roof of the facility for use with the NASA SEMA program, primarily for middle and high school kids to look at live weather data and play around with it, but it's not functional data because it's getting the data off of a building roof. And you need to be out in an environment like this where you're on a grassed irrigated location where the weather station actually is comparable to any nearby agricultural production fields. And you might also take other temperature. If I'm a vineyard manager, I'm not only interested in the air temperature, I'm interested in my canopy air temperature. What's the temperature under the leaves inside my canopy? So it can get even more complicated, more data points depending on what kind of crop you're growing. Here's a very poor CIMIS station. I don't know if this is one that was not a CIMIS station or one that was maybe decommissioned and is still sitting there, or was still sitting there in 2002. But this was not what you want for a CIMIS station. It should be on an irrigated site. Again, not a good situation. It's not being sited on grass. Yeah, it's nearby. So people build their own stations and set them up. And so I'm guessing that the last one and this one are things that people have done themselves. They just don't look like they would have been decommissioned CIMA stations. They just look like somebody's personal station that doesn't quite fit the bill for an accurate California Irrigation Management Information System site. Oh, and this slideshow, it's not CIMAS anyway, it's Colorado, so they don't have the same rules, but they have the same science. But I don't know what their state system would be. And there's the AZMET, A-Z-M-E-T, AZMET, the Arizona Meteorological Network, I think it's called. And it's stationed through the, I think, University of Phoenix. You could just type in A-Z-M-E-T, AZMET, and I guarantee you could get to their site very easily, just like our own CIMAS here in California. Weather station location and density. Various studies suggest weather station spacing of 20 to 40 miles to maintain a 0.9 spatial cross correlation for reference ET estimates. So you don't want to go too far, 20 to 40 miles, the distance between stations, and you can average or do a weighted average if you're between the stations. And I would do that all the time in Salinas. I would take the North Salinas, South Salinas stations, and depending on where I was, I would either use one station, the other station, or some sort of an average or weighted average between the two. If I was kind of near the North Station, I might use 80% North Station, 20% South Station, and just average the numbers out. Close enough. If you really need solid data that's accurate for your site that is more than that, you need your own weather station. So in summary, evapotranspiration is a key component to determining irrigation water requirements. The most direct methods have limited practical application. Pretty damn hard to make one of those lysimeters or doing some of the other direct methods. They're interesting from a scientific standpoint. They're interesting from getting a raw data to calculating these crop coefficients and things. A lot of work has gone into these lysimeters, but they're not useful to the average grower. The average grower needs to just plug data in and use the information that comes off of a mathematical model and adjust it. And there's nothing else I want to point out there. There is something, though, that I want to point out that I thought I left in here. Maybe I just always brought that up on a slide. Let me see, crop coefficient graph. So here's some images of crop coefficients. And you can see, as an example, in a very young crop, you might have the crop coefficient starting out way the heck down here at 0.3 or 0.29. I can't see exactly where that is. And then it will rapidly go up during crop development, crop growth, and peak out at about, what is this, 1.1, and then start nearing maturity, late season, it'll start going back down again. And this is pretty common. So you can see a similar thing happening here in the corn. They tend to follow those patterns. But in the real world, it's not a nice squared off graph like that. The real world will have some of these curves. And so you need to look up these curves for your crop. What is your crop coefficient curve? And here's one that has a generic model in red with an averaged measurements in this curved line and actual data points in the black dots. And now that's talking about light interception, but the same thing happens. The same exact pattern happens. Here's another graph showing very similar types of patterns. And the graphs are going to look similar, but they're going to change dramatically in the details, whether you're growing rice or spinach or grapes or whatever else. You need a good crop coefficient, and they're based on where am I in the growth of my crop, and how much ground cover, how much ground, if I took an aerial photo, what percentage of the ground is showing versus the ground is shaded by canopy. Those are the types of things that go into trying to place yourself on this curve, because you can't really just do days, especially in lettuce or something. Days is very different in a crop planted in March versus a crop planted in June. The number of days to rapid growth is very different. So you need to find out ways to get that crop coefficient. And that is challenging. That is challenging. And that's part of the biggest challenge in development of these graphs to estimate what crop coefficient am I going to use. You can calculate your crop ET, or excuse me, you can calculate your reference ET very easily. That's the easy part. But now I need to multiply it by some magic number called the crop coefficient to get my actual crop ET. And that takes some experience and some knowledge about these crop coefficient graphs. And you have to pick, where is mine going to be? Where am I in my crop? Got to read some papers to do that. All right.